In this video, we're learning about antidifferentiation, which is derivatives, but in reverse. Now, it's also called integration. That's a more common name for it. And you might be wondering what this has to do with the last video, which was about area under the curve. Turns out it has a lot to do with that, and we'll find out why very soon. But for now, we just have to practice these rules of calculating integrals. These are the same rules as your derivatives, they're just in reverse. Okay, so let's do an example first, but pretend we don't know any of those rules. F dash is 2x. What was the original function? So the original function, if you think about your rules of derivatives for a little bit, you might get that it was x squared. Because if you think about differentiating that, the way you would differentiate x squared is you would bring 2 out the front, and the new power would be 1. So essentially, you just don't write it in. And hey, look, f dash of x is 2x. That's what we needed. Good stuff. But what about f of x equals x squared plus 7? Well, the derivative of that is 2x. So there's another answer. Cool, it could be either of those things. In general, it doesn't matter what number you put on the end. X squared plus c is the general answer. So that is just all the answers that you could possibly have. It's x squared plus any number you want on the end. And as long as you've done that, then the derivative of this thing will just be 2x. Cool. All right, now let's look geometrically why that's true. So I've got here the graph of x squared. Now the way that you would interpret the derivative is if we look at this point where x is 1, that red line, the original function, has a slope of 2 because the derivative there has a height of 2. So the value of the derivative at x equals 1 is 2. It gives you the slope. If we look at x squared plus c, then the derivative of that, x squared plus c, should overlap that blue line. Probably be more obvious if I made a different color like purple. You can see that no matter what c is, the derivative doesn't change. And even if c moves up and down, the slope at any x value is not changing. And if I just wait for it to come back up and then pause on a specific value, at this point here, where x is 1, the slope is still 2. Same as a red line. When x is 1, the slope is still 2. C only changes by moving the graph up and down, just moving. It doesn't change the slope of the graph at all at that point. Okay, so that's sort of what the plus c is all about. And we can write this in a nice concise statement. We can say that the integral of 2x with respect to x is x squared plus c. So that's what it means. Now, the integral thing here, if we took f and we differentiated it, so usually we write that as like d by dx or whatever, then we get the derivative. Integrals are the opposite of that. So the integral is the opposite of the derivative. Okay, let's do some examples. So we want to integrate x squared. So if we are familiar with something like x to the 7, and I differentiate that, I'm going to get 7x to the 6. By the way, if I integrate 7x to the 6, I get x to the 7. There's just a general rule for it. So you raise the power up by 1, and then you divide by that number. And that's going to be the very first rule, well, the second rule on our integral table there. Now, just in case you don't believe me that that is the integral, we imagine taking a function like x cubed over 3. The plus c value doesn't matter too much. If I want the derivative of that, it's going to be 3x squared over 3. The 3's will cancel, and you got x squared. So I've managed to get the thing that I started with. Okay, integral of x cubed. It's x to the 4 over 4. C is in R. Never ever forget to write the plus c, very important. Integral of 5x4, let's apply our rule. 5x to the 5 over 5. And then you can actually simplify this down a little bit because the 5's will cancel off. And you're left with x to the 5. Okay, integral of this whole thing. Turns out that you can do integrals term by term. So the first term is going to be 2x to the 5 over 5. Next term is going to be 3x. The old power was 1, so the new power is 1 more. It's 2. And plus 1. If I think, what function do I differentiate to get just a constant, which is 1? You might be able to spot it. The answer is x. Or if you want, there is an actual rule for this. So right up the top of that table, integral of a constant is that constant times x. By the way, all these integral rules need plus c when you write them out. I just didn't want to clutter up the table too much. Okay. Good stuff. Speaking of, our integral here needs plus c. Next one, 3x plus 1 to the 5. Now, this is a special case. It works a little bit like the chain rule, but not quite. So you do get 3x plus 1 to the power of 6, all over 6. So it's sort of like that normal rule there. And you've got to times it by 1 over the number with x. So that number was 3, and 1 over 3. If you're familiar with the chain rule for derivatives, this works very similar to the chain rule. This only works if the thing in there is a linear function, like ax plus b. It does not work if you have anything more complicated. And in general, integrals are a little bit harder than derivatives because some integrals you just can't do. But generally, if you're asked to do an integral, you will be able to do it in like a test or something. Okay, so you can see that we've got the x to the n rule, does that. And the corresponding rule is a linear function to the power of n. You still raise the power and divide by that new number. You just times by 1 over a, 1 over the number with x. Okay. Next one, 3x cubed plus 1 to the power of 5. I'm basically going to say that that's not super realistic to do at the moment. And the reason is linear was good in here. This is a cubic, which makes me very upset. The actual way to do this integral would be to expand it out. So you're going to get like 6 terms using like the big Pascal's triangle super duper expansion, and then integrate it term by term. Now, I'm not going to put you through that in this video. So there's no shortcut to that one. Okay, integrals with index laws. So this just becomes 3x to the power of minus 2. We can raise the power up. So this is 3x to the minus 1 over minus 1. Be very careful. You're adding 1 to the power, so minus 2 will go up to minus 1. If you want, you can write this as minus 3 over x, if you want to make that just that a little bit simpler. Okay, root x becomes x to the power of a half. So what's 1 more than a half? Well, it is 3 halves. Now you do need to divide by 3 halves as well. Dividing by 3 halves is the same as timesing by 2/3. So I'm just going to write that to make it a little bit cleaner. There we go. 1 over x. Okay, so let's apply our index laws. So this becomes x to the minus 1. And then we need to raise up the power. So we're going to get x to the power of 0 over 0. Oh no. Okay, that should ring alarm bells. We can't divide by 0 in maths. Something has gone horribly wrong with this. All right, so I'll let you think about maybe, can you think of a function that when you do the derivative to that, you get 1 over x? There is a function that we know that does that. Pause the video if you want to have a think. If not, I'll give it away. That function is the log of x, ln of x. So that was a rule that we had. So the actual correct way to do this should be the integral of 1 over x is log of x plus c. C is a real number. Done. Technically, this only works for x is strictly greater than 0. And that's because log doesn't like negative numbers in it. Okay, so that is the weird case. Basically, as long as you have like integral of 1 over x to any power, generally what you can do is write this as x to the minus n, and then it just becomes x to the minus n plus 1 over minus n plus 1. So that rule almost always works, just as long as n's not 1. If n equals 1, you have to do this log thing. It's a bit of a weird case. Okay, e to the x. So the integral is e to the x. Now that's a direct rule, but if you remember, like the derivative of e to the x was e to the x. So the integral doesn't change much. This becomes e to the 2x plus 3 times a half out the front. So you divide by the number that's with the x there. Now, again, this only works nicely if the thing up on top of this e is a linear function, like 2x plus 3. E to the power of x squared is actually impossible. And it's not just that we don't know how to do it yet, it's that we can't do it, which is wild. Mathematicians did call this solution like a new thing. They defined it. I think it's called like root of x or something. So they defined a new function, which is the answer to this. But if you want to write this down in terms of like e's or sines or x's or square roots or whatever, you can't do it with the symbols we currently use in maths. So they had to define a whole new function. The weird thing about integrals though, we won't do this in this video, but the integral of this is absolutely possible to do. Integrals are very weird like that. Okay, trig integrals. Sine goes up to minus cos. Don't get thrown by the minus signs. They're sort of in reverse for integrals. Because if you think about it, cos differentiates to minus sine. So sine should go up to minus cos. Cos goes up to sine. If you have some big old messy function like this one, so sine will go up to minus cos, so you get minus 3 cos of 4x. I have to divide by the number with x, so that's 4. Cos will go up to normal sine, so I'm going to get minus 2 sine of minus 2x plus 1, all over minus 2. And then I can probably simplify this down a little bit. So minus 3 cos of 4x over 4, and then this will just become plus normal sine of minus 2x plus 1. Yeah, you're only allowed to do stuff like this if the thing inside the sine or the cos is a linear function, ax plus b. Anything messier, like a sine of x squared, can't do it. All right, one more example. So it turns out you can sometimes find the c value. So that is the derivative of f. So f of x should equal the integral of 6x squared. And we can work out what that is. It's 6x cubed over 3. And then that's just 2x cubed plus c. So that is the function itself. If you happen to know a point on the function, like what this is saying is that the point 1,4 is on the function, much like our example before, when the function could be any vertical translation, if we happen to know a point on that function, then that sort of tells you where it is up and down. So in our case here, we know that the point 1, 4 is on that graph. So when x is 1, y is 4, and we can sub that in to find the c value. So you're going to get 4 is 2 plus c, so c is 2. So the function is 2x cubed plus, and now we know what the c value is, it's 2. So just be aware that can come up.